Thanks for the introduction. And this is joint work with Georgios Fotiadis, Johan Gross-Shadow, and Daniel Page. So as the successor of AVX and AVX2, AVX 512 is the third generation of the Intel Advanced Vector Extension family and follows single instruction multiple data, the SIMD paradigm. As indicated by the name, AVX 512 supports the instructions to operate on the vectors up to 512 bits. And in this work, we are particularly interested in one sub-extension of it, namely the AVX 512 IFMA. And here, the IFMA is the acronym of the integer fused multiply add, and designed for the big number multiplication to accelerate the relevant crypto algorithms, such as RSA and ECC. And one important feature of the IFMA is the vector multipliers are 52-bit wide. So this means you have to use 64-bit element, and the 512-bit vector is divided into 8 lanes. And in this work, we take advantage of the 64-bit times 8 lanes SIMD computing power to implement the target pairing. And the IFMA extension includes actually only 2 instructions, and both of them first multiply the 8 52-bit elements of the vector A with another 8 52-bit elements with vector B and then it has either the lower or the higher halves of the 8 resulting 104-bit products and to add with the another 64-bit element of vector C. But currently the IFMA is only supported on a small fraction of the Intel CPUs. For example, it's not supported on the Intel core CPUs using the hybrid architecture such as Alder Lake. But early this year, Intel announced that they will integrate the 512-bit IFMA instructions to all future CPUs in the Intel AVX 10 technical report. So in this work, we use the Intel Isolate core processor, and the IFMA instructions on this CPU has a CPI of 1 and the latency of 4 clock cycles. So after introducing the hardware part, we take a look at the algorithm. So pairings play an important role in the cryptography. So for example, there are many applications based on them, such as BLS short signature, the KZG polynomial commitment, and Gross 16 zero-knowledge proof systems, and advanced PKE schemes. And this work we focus specifically on the optimal 8 pairing on BLS 12381. And it's included in the RETF reference specification and used in the Ethereum Pecan chain protocol and also the Ethereum KZG commitment. In addition, Zcash also upgrades to the BLS 12381. Some basic information about this curve. So it's a member of the BLS 12 family of the curves with embedded degree 12. And the elliptic curve is defined in this form with the 881-bit prime P. And it has a composite order and admits degree 6 twist, which enables efficient optimal 8 pairing. And the optimal 8 pairing needs the input of 2 points Q and P of the order R and is computed in this way. And the optimal 8 pairing contains mainly 2 steps, namely the meter loop and the final exponentiation. And they were computed with the arithmetic operations in the FP212. And the important operations include the multiplication, squaring, cyclotomic squaring, and sparse multiplication. And the FP212 operation is computed via the tower extension. And here in this work, we have 2 different tower extensions. And the difference between them is the middle layer. So one is the FP26, and the other is FP24. And apart from the FP212 operation, there are also some elliptic curve arithmetic. For example, the point doubling, point addition, the line computation, the line evaluation. So let's now go into the detail of the Miller loop and the final exponentiation. So as indicated by the name, the Miller loop is a loop. And then in each iteration, there are basically 2 different types of the steps. So one is doubling step. It includes a point doubling, line computation, line evaluation, and the update of the Miller function. And the other one is the addition step, so which includes the point addition, line computation, evaluation, and the update of the mirror loop. And because the seed is the negative, so the last operation is to do the inversion of the mirror function. As for the final exponentiation, so the computation is usually split into two parts, namely the easy part and the hard part. So as indicated in the name, we know the hard part is more difficult to compute. And there exist some different formulas for computing the hard part. And here, in this work, we use specifically this one to compute the hard part. So when coming to the practical implementation, there exists a multilingual BLS 12381 signature library named BLAST, and it's currently integrated in Ethereum, so it's really widely used and popular. And based on that, we use x64 assembly implementation of the optimal 8 pairing contained in this library as the baseline implementation in this work. And from the last slide, we know both the mirror loop and the final exponentiation exhibit a strong data dependency, so they are not seen differently. However, the FP212 and elliptic curve operations they use internally are seen differently. So in this work, our target operations are these sub-operations. And then we carried out a profiling process for the baseline implementation. And here are what the profiling results look like. We listed 6 performance critical operations, and notably, the first one, the FP212 cyclotomic squaring, takes more than 70% of the execution time of the final exponentiation. Let's then have a look at another scalar implementation which was presented 2 years ago by Longa, also in CHES. And this implementation used the relic library as a base implementation and mainly optimizes the virus extension field modifications and is slightly faster than the BLAST library, mainly due to the use of the compressed cyclotomic squaring. So to make it clear, the BLAST library uses the uncompressed cyclotomic squaring, which was proposed by Geringer and Scott. And longest implementation, or we say the relic library, used the compressed cyclotomic squaring, which was proposed by Arena et al. So the difference between these two versions is in the computation of the consecutive squarings. The compressed version computes only 2 coefficients, B and C, while the uncompressed version needs to compute 3 coefficients, A, B, and C. And then after the consecutive squarings, the compressed version requires 1 FP square inversion to do the parallel decompressions to retrieve the missing component A. And the point is, in this decompression, there exist 2 different formulas depending on whether B0 equals to 0 or not. And the case that B0 equals to 0 has the negligible probability. So in the practical implementation of the relic library, this case is not considered. So if we apply the same strategy and use the same the compressed cyclotomic squaring implementation in the BLAST, then the BLAST becomes slightly faster. About our vectorization, so we know the FP212 operation is computed via the tower extension, and the bottom 2 layers are the prime field FP and the quadratic extension field FP square. So our vectorization on these 2 layers are based on our previous work presented in CHES 2022, which is a vectorized implementation of Psych. And this time we have to do some necessary modifications, such as using the 48-bit per limb representation and use the prime P of the BLS 12381 curve. And likewise, we use also 2 different types of the prime field implementations, the 8 times one-way and 4 times two-way. So what does it mean? So taking the 4 times two-way multiplication as example, so it computes 4 multiplications in parallel, and each multiplication uses 2 lengths of the vector. And based on these 2 FP implementation, we developed 4 different FP square implementations. And we take the FP square multiplication as an example. And here on this slide, we show the two-way and four-way vectorization of it. And both of them use the schoolbook method for the implementation, which is more efficient than Kurotsuba's method in these two cases. Okay, now let's have a look at the first FP212 operation, which is FP212 cyclotomic squaring. And here we are considering the uncompressed version, so which was proposed by Granger and Scott. So we also call it Granger-Scott squaring. And actually, the Granger-Scott squaring is not well suited for either the two-way or the four-way vectorization, because we can see the underlying, the number of the underlying FP24 squaring is 3. And then we develop a hybrid vectorization for this FP212 cyclotomic squaring, so which means we compute the coefficient A in one way, while the other two coefficients B and C are parallelized in two way. So the only FP24 operations that we need to vectorize is then the FP24 squaring. And here it also has like two squarings and one multiplication. So we take advantage again the hybrid vectorization to implement it. So we use two-way parallelized squaring and one-way multiplication to implement it. So recall that we have two different versions of the FP24 squaring. So for the two times 2 times 2 times one way, we use this combination. And then for the 1 times 2 times 2 times two way, we use a different combination. Okay, then we look at another FP212 operation, which is the FP212 multiplication. So the difference between the FP212, the important difference is this time it uses a different, the tower extension. So where the middle layer is FP26 instead of FP24. So let's assume the alpha and the beta are two FP212 elements. Then the multiplication will consist of 3 FP26 multiplication if the Kurotsuba's method is used. And then we zoom in the FP26 multiplication, and if we take advantage of the 3-way Kurotsuba method, it will contain only 6 FP square multiplications. And here on the right-hand side, we show the two-way vectorization of the FP26 multiplication using this 3-way Kurotsuba. And we can see the lengths are almost fully used except the last operation. We also developed the vectorized implementation for the FP212 sparse multiplication and FP212 squaring. And then we benchmarked them, the scalar and the vector implementations on our isolated core CPU. And our vectorized software library is called AVXBLS. And from the graph, we can see the speed up factors of our vectorized implementation range from 1.85 to 2.26. And as described before, we use this hybrid vectorization for some operations. And notably, some subroutines are still non-vectorized due to the code dependency, for example, the FP square inversion. Now what are left are the elliptic curve arithmetic operations. Here we use the doubling step as example, so it includes 4 different steps, as we said before. And here, in the baseline implementation, the point doubling, the first 2 steps, the point doubling and line computation is developed as a dedicated function named line underline DBL. And the computation is basically these 2 equations. And here we list the cost for both the scalar and the vector implementations of the line DBL and the line ADD. So line ADD means the point addition and line computation. And then on the right-hand side, we show the speed up factors. And we can see the line DBL has a higher speed up than the line ADD. The reason is because the line DBL is vectorized in 4-way, while the addition is vectorized in 2-way. So here we show the 2-way and 4-way vectorization for the line doubling. And I highlighted the costly operations, for example, the squaring and the multiplication. And on the left-hand side, we can see there exist two-way multiplication and 4 two-way squaring. And then when translated to the 4 vectorization, it has 1 4-way multiplication and 2 two-way squaring. And the big advantage in the 4-way vectorization is at the bottom layer, it can use the 8 times 1-way prime field multiplication, which is much more efficient than the 4 times 2-way FP implementation. And then after implementing the target operations, here we benchmark the pairing implementation of the 4 different implementations. And from the graph, we can see the AVX512 offers the significant performance gain for the pairing computation. And our vectorized implementation achieves 1.86 speed up for the optimoid pairing on the BLS 12381. And the speed up can be further improved to 1.97 if we use the compressed cyclotomic squaring. And then we compare our work with our previous DeSyc implementation. So the AVX library includes the IFMA implementation of the isogeny-based key establishment algorithm Cyc, and it's developed also by us. And this time we benchmark them on the same CPU, so which means we can have a relatively straightforward comparison. And notably, the Cyc implementation achieved the higher speedups. For example, 3.21 for the encapsulation and 2.45 for the decapsulation. And why the speedup is higher? Because the pairing implementation needs the pairing needs FP212 tower extension, and the tower extension needs more field reductions compared to the FP square arithmetic used by Cyc. And also Cyc allows better parallelization at higher layers. For example, the 8-way parallelization is possible for the 3 isogeny evaluations, but in this work, the 8-way parallelization is only possible at the prime field layer in the AVX-BLS. So to summarize this work, so AVX512 is very useful for the pairing computation. And from our virus vectorization attempts, it shows the 8 parallel lines seem to be an ideal setup. So in contrast, for example, the 16 lanes would already result in many lanes being idle. And our vectorization strategies can be adapted to other vector extensions. And our source code is publicly available online at the GitHub. And for the future work, we will look at the complete BLS signature and to do the vectorization implementation of the complete BLS signature. And we will also take into account the multiprocessing computing power and to research the optimal vectorization plus multiprocessing strategies for either the pairing or the BLS signature. That's it. So thank you very much for your attention.
Any question? I have one question about the future work you mentioned, speaking about the parallel, the last topic that we were saying, speaking about exploiting the parallelization together with your optimization.
Yeah.
Where do you see the main challenge there?
So the multiprocessing has a different computing paradigm, so it's not single instruction, multiple data. And then, so actually we have some rough ideas, like because a mirror loop, because there already exists some, the existing work that use the multiprocessing to accelerate the mirror loop. Because in this work, we did not vectorize the mirror loop itself. We vectorized the sub operation. So our plan was to try to combine these 2 different types of the vector computing power for the components. So it's like depends on the structure of the primitives. Yeah.
Okay. time for another question. If not, can you also elaborate about the second future work that you actually mentioned as the first, to look at the complete signature? Do you see any particular challenge over there, or it's more or less an engineering straightforward extension of what you already presented here?
Well, so actually this is the ongoing work now. So apart from the pairing, there is another important operation named hash-to-curve. And in this operation, it needs the different, for example, at least the elliptic curve operations, and which uses the different formulas and something. So here, for sure, there is some space that we should explore. For example, to use the different coordinates or the formulas.
If there are no more questions, I would like to thank the speaker again.
Thanks.
The next talk of the session is Accelerating DSA Signature Verification with Faster Scalar Size Halving, and will be given by Hanvar Hassan from University of Waterloo. Please welcome Hanvar to the stage.
So this talk has basically two parts. One deals with faster scalar size halving, and the other part is to deal with verification of EDDS signature. Just to set up the context here, especially if you have attended the keynote talk this afternoon, okay? So for this talk, there is no hardware, no ASIC, no FPGA. And here, this topic of EDDS signature verification is very well researched. So keep that in mind as you see the improvement results here. So I guess to this audience, it's well known that elliptic curve digital signatures are widely used in various applications. The main reason is that this kind of signatures require shorter keys and also have better performance. And then applications include, especially notable applications these days, are blockchains like EDDSA or digital signatures can be found, for example, in Ripple's XRP, or ECDSA is used in, say, Bitcoin and Ethereum. One of the most commonly used elliptic curve signatures in practical applications is EDDSA. There's some advantages of using EDDSA over its counterpart ECDSA, which is a bit older than EDDSA. For EDDSA signatures, we need computationally expensive scalar multiplications. And depending on the size, the cost can be quite high. For example, if we have a scalar that's 256 bits long, then a single scalar multiplication will require more than 350 elliptic curve operations. And this 350 elliptic curve operations will in turn require more than 3,000 finite field multiplications. So it's quite an expensive operation. On the other hand, like there are opportunities for some optimization. So if we can combine, say, two scalar multiplications, then we can use better algorithms. For example, we can use DSM, double scalar multiplication. Or if we can combine three scalar multiplications together, then we can use triple scalar multiplications. When we have more scalar multiplications, something that we can find in badge signature verification, then we can use like Bose-Coster algorithm. And if we even have more scalar multiplications to deal with together, then algorithm like Pippenger method could be very, very useful. Verifying an EDDSS signature requires two scalar multiplications. So suppose we have this sigma, the point R and S signature, and this is on message M or public key A. And say we know order L of the elliptic curve group. Then to verify this signature, first we compute the hash value H using point R, point A, and point M, or message M. Then we check this equality. We check whether R is equal to SB minus HA. Okay? So here we have two scalar multiplications. One is SB, another is HA. Here, the length of scalar S and H is roughly equal to the length, bit length of the order L. So if, say, order L corresponds to 2B bits, then actually we call it a full scalar size, or the scalars are full length. So for example, for ED 255-19 curves, this 2B would represent close to 253 bits. So when we have this L of 256 bits long, the straightforward use of DSM, which I referred in the previous slide, double scalar multiplication algorithm, then right-hand side of equation 1 will require about 450 elliptic curve point operations. Majority of these operations are actually point doubling. So if you want to really improve the performance of this kind of signature verification using DSM algorithms, then one way to do it is to reduce the number of doubling that's involved here. And to reduce number of doubling, an easy way is to reduce the length of the scalars. And here the scalars are S and H. So if you can reduce the length of the scalars, then we should be able to reduce the number of doublings, and we should be seeing the improvement in the performance of signature verification. Now, just reducing length of only one scalar would not be enough. We have to actually reduce the maximum length of these two scalars. And there are a number of ways to do it. So here, let me first talk about the concept of half-size scalars. So consider we are dealing with this multi-scalar multiplication situation indicated here, this summation k sub I, p sub I. So we call the integer k sub I a half-size scalar if the bit length of k sub I is less than or approximately half of the length of the base point order. So if L is of 256 bit long, then an integer like k sub I is half-size scalar if its length is half of that, meaning 128 bits or less. So we want to actually get this kind of half-size scalars for our scalar multiplication, especially in the context of signature verification. So here the problem is this. Given L, which is the order of the curve, and H, which is the hash value that I referred in the previous slide, and assume that L and H are co-prime. Of course, in practice, this is the case. We want to produce two half-size scalars or integers, rho and tau, such that rho is congruent to tau times h mod L. Okay. There are ways to do it, and in the literature, what you find, okay, like to reduce size of the scalars to something like half of the length of base point order, you can use extended Euclidean algorithm, which is very well known. One can also use Lagrangian algorithm for basis reduction of two-dimensional lattices. And actually, this idea has been was proposed probably about 20 years ago when Antip et al. Were trying to improve the performance of ECDSA signature verifications. So my next slide, here I have very classical extended Euclidean algorithm. And as this audience know, that for extended Euclidean algorithm, say we have two integers input, L and V. And the output of this extended Euclidean algorithm will be GCD of L and V, which is here denoted as R. And there will be two additional integers as output, denoted here as S and T. And this relationship that you see at the end of that line, R is equal to SL plus TV, this should hold. So when this algorithm is executed, in line one, we're actually initializing some variables. There are three sets of variables. First set of variables are R, and labeled as R minus 1 and R0. Then the other set is S variables, and finally we have T variables. Things to note here, the initial values of variables R are close to, for example, like 100 and 256 bit long if L is 256 bit long. On the other hand, the length of T variables is just a 0. As you can see, initially T minus 1 is initialized with 0, and T0 is initialized with 1. As the algorithm progresses, the bit length of R variables actually decreases from length L to almost 0. On the other hand, the bit length of T variables increases from 0 all the way up to the length of L. And when the algorithm actually terminates, the relationships that you see at the end of output, that means R is equal to SL plus TV, if you take mod L on that, that becomes R congruent TV. Okay? So here, like at the end, R will be really the GCD of the two inputs, and T is the byproduct of this algorithm, and V is the other input. So this is actually a relationship that I was showing in the previous slide. But the problem here is that we do not know what is the length of R or what is the length of T. We want to have length of R and length of T equal to half of the length of L. And that can be achieved simply by changing or stopping this algorithm halfway. So as length of T increases and length of T increases and length of R decreases, if you can stop middle way, then we can expect to see that length of R and length of T is about half the length of L. Okay? And this is exactly what Antip et al. Used in their effort to speed up the signature verification of ECDSA algorithm. And this is really shown in line number 2. If we just change the stop condition, then this algorithm will produce two half-size scalars. And this is actually indicated also in the second line with output. So here we do not have GCD as output, rather we have RST, and RST has the relationship that's shown on that line with the R is equal to ST, SL plus TV. And if you take mod L, then R is congruent to TV. And since we are stopping halfway, the length of R is half of length of L. Similarly, length of T is half of length of L. And this is exactly what we want, so that we'll be able to reduce the number of point doubling in double scalar multiplication needed in the verification of EDDS's signature. So if you look at the algorithm here, this algorithm is giving actually the correct size for variable L and variable T, but the most expensive step in this algorithm is actually step number 4, where we're actually determining quotient. And for large variables, for variables that deals with say, large numbers, this could be quite an expensive operation. And because of this, actually, until this work, people have avoided use of external Euclidean algorithm to come to actually improve the speed of ECDSA or EDDSA signature verification. As I mentioned, one alternative to external Euclidean algorithm for generating half-size scalar is to use Lagrange's algorithm. And about 10 years ago or so, Thomas Pornin came up with an algorithm for coming up with the half-size scalars using Lagrange's algorithm, but that algorithm also requires this kind of division operation. So he actually devised a division-free algorithm, a division-free version of Lagrange's algorithm, and that actually helped to speed up the verification of SNOR and EDDSA signatures. For some reason, Thomas Pornin's work did not actually look at applying the same technique to external Euclidean algorithm to have a division-free version of it. So in our paper, you'll find a division-free, two versions of division-free of external Euclidean algorithm. And by having division-free algorithm for extended division-free steps for external Euclidean algorithm, we can actually speed up the half-size scalar generation significantly. But before I talk about this performance, let's first see how these two algorithms are producing those half-size scalars. We are interested in having length of R and T, which would be half of length of L. So in my next slide, I'll show you how these two algorithms are actually achieving this. So these two algorithms are denoted as HEA approximate Q. So this is really approximate quotient-based half external Euclidean algorithm. And the other method, due to Pornin, is labeled as reduced basis. So this slide shows the size of those two scalars, and they are shown under this reduced basis and approximate Q basis of half external Euclidean algorithm. So, and this is for two. The first one is for ED 25519 instance of EDDSA. So here we have length L is equal to 253 bits. And as you can see in that row, length of row for reduced basis is on average 125, and more or less same thing for the other algorithm. Similarly, length of tau is 125, and for the other is 124 and 123.9. So they're very similar, and they are very close to half of length of L. We've also done a similar experiment with the other instance of EDDSA. That means this Edward curve 448. And here the length of L is 446. And this half-size scalar that we're producing are actually truly half size, okay, just a little less than. But there are some tricks that we can use to actually increase the size of these two scalars. So given that two algorithms are generating good size scalars, but how about the performance? So this table shows the cycle counts of these two algorithms for those two curves, ED25519 and ED448. And these tables indicate the cycle counts for those three algorithms. The rightmost column indicates the improvement. What you can see here, compared to reduced basis algorithm, approximate Q-based half-extended Euclidean algorithm is much more efficient, much more, it takes a lot less cycles. The reason behind is this: Lagrangian algorithm requires more variables in its loop, and also some of the variables are much longer than what we need in an Euclidean algorithm. The details are in the paper. Now that we have this half-size external Euclidean half-size scalars, how to actually use them in signature verification. So first I'll talk about individual verification. So the equation that you see in the top line is for verifying an individual signature. And this could be done using double scalar multiplication algorithm. And now if we apply that half external Euclidean algorithm on H, that will give us two scalars, two half-size scalars, rho and tau. Multiply the equation in the line at the top with tau, then equation number 2 is what you obtain. The important thing to note in equation 2 is that both scalars, tau and rho, are half-size scalars. And what we have at the left, see B is a system parameter, is the base point, so there could be pre-computation done for the left-hand side. But we could do a little bit better. Actually, after multiplying tau and S, and then taking mod L, we can then actually split the result into two parts, the lower B bits and the higher B bits. That will actually give us what you see in equation number 3. And here B prime is really a pre-computed point because B is known, and B prime is 2 to the power B to the small b times B. The point here is that equation number 3 is a quadruple scalar multiplication. Here we have 4 scalar multiplications, but in each scalar that we have here, the length is half of the length of order L. Okay, and that's why actually the speed of this algorithm comes from. So here we have a quick comparison. We have implemented this new algorithm, or the new quadratic scalar multiplication-based verification that I showed you in the previous slide, and the traditional or classical double scalar multiplication-based verification. So there are two actually rows in the table. The top row uses pre-computation just based on B, and the lower row increases the pre-computation by factor of 2, and we can expect better results. But very quickly, See, this comparison is for individual verification using ED25519 donor libraries. This is this is an open source and highly optimized implementation. And as you can see in the middle column there, the improvement for just a pre-computation, B-based pre-computation is 16%. And if you increase the pre-computation, then the improvement goes to 20%. And the second rightmost column indicates some recent results that we obtained after publishing the paper. So with that results, the improvement actually goes even a little bit more. So that's for individual verification. Now very quickly about batch verification. So when we have many EDSS signatures to verify, then things could be really, really resource intensive. To address this, we can use batch verification. In batch verification, signatures are batched and then verified together. And this kind of batch verification has very useful applications in systems like blockchain networks. So here, this is a classical approach. Suppose we have n signatures, and these are shown on the screen is sigma sub n. And we want to verify this n signature, and these signatures can be combined. And for security reasons, these signatures are combined after doing some randomization. So each individual batch verification signature batch verification equation is actually multiplied with a random number z sub I. And if we sum them up, then equation number 4 is what we get. So if you look at the equation or the expression, you will be seeing that there are actually multiple multiscalar multiplication. One is involving A sub I, another one is involving R sub I. So here we have a case of multiscalar multiplication involving 2n scalar multiplications. And for this, people normally would use Bose-Coster algorithm. But here, the coefficient of A sub I is just a full-size scalar. And this doesn't really help us to reduce the cost, reduce the number of doubling in the operation. So we want to actually apply the half-size scalar algorithm that I mentioned earlier. But see, that algorithm that I mentioned earlier doesn't really work very well when we have a situation like what is shown in question number 5. Here, the coefficient of Ri is Zi, and coefficient of Ai is Zi times Hi. For the half-size scale algorithm to be useful, the coefficient of R sub I needs to be unity, but this is not the case. So we have devised a new way to randomize this algorithm. For the lack of time, I'll just quickly go through the steps. In step number 1, we choose a 2-bit random integer, say u, and compute multiplicative inverse of u, which is denoted here as u prime. And then we call that approximate Q-based half external nuclear algorithm with input L and VI. VI is the product of hash value HI for signature I and U prime. And the algorithm gives 2 half-size scalars, rho I and tau I. And then we multiply the verification equation of ith signature with tau I. And once we do that and simplify, equation 6 is what we get. If you look at equation 6, the coefficient of A sub I is u times rho I. But if you just ignore u for the time being, rho I is half-size scalar. Similarly, the coefficient of R sub I is tau I, which is also half-size scalar. So for n signatures, we add all these equations, then equation number 7 is what we get. So here, if you look at the very right end of that equation, or part of this expression, you'll be right-hand side of that equation, you will be seeing that after U, we have something in the bracket. That's really a case of multiscalar multiplication. And the result is denoted by A. But here, the scalars, rho I, half-size scalar. Similarly, we have another instance of multiscalar multiplication, and that is indicated with capital R in red after this curly bracket. And again, there we have half-size scalar. So here, because of this half-size scalars, the computation is much faster than what normally would get when we have full-size scalars. Once we have evaluated equation number 7, then what we will get is really shown in the second bottom line, S sub B, where S is the product of these two scalars that you see, and then the sum up. And at the right-hand side, you have R plus UA. A is a point, R is a point, U is an integer. So here again, we have an instance of scalar multiplication with full-size scalars. We apply our algorithm again the way we have done for individual verification. Then we should get an expression where we will have only half-size scalars. So with that one, then actually we can verify a batch of n signatures efficiently. Very quickly, I'll show you some of the timing results that we have reported in the paper. So this compares the classical approach and our approach for various batch sizes. So at the leftmost column, we have batch sizes. And the next column is as for classical approach, indicating the number of cycle counts, and then our approach. So what we have seen is that our approach outperforms the classical approach from batch sizes of 7 and up. So this just my last slide. So for EDDSA verification, okay, our work presents significant performance improvement given the context that I mentioned at the very beginning of this talk. The proposed approximate quotient-based halfway extended Euclidean algorithm can also be used for computing multiplicative inverses, and the details are in the paper. And our software implementation is available as an open source on our GitHub side. Currently, we are extending our batch verification approach, okay, to ECDSA. Okay. Thank you very much.
We have time for one quick question. And then I have one. You started the talk saying there is no hardware in this work. Where do you see hardware helping?
Well, see, that halfway extended Euclidean algorithm is kind of like overhead to regular verification process. So if someone has a hardware to implement that Euclidean algorithm, that would help. Because each time a verification process is done, we need to do we need to execute the extended Euclidean algorithm halfway.
Thanks. Then let's thank the speaker again. The next talk is Fusion MSM, a collision-free and arithmetic-optimized FPGA-based accelerator for MSM, and will be given by Cheng Chen from Shandong University. Thanks, Cheng Chen.
Okay, thank you for your introduction, and good afternoon. My name is Chen Cheng from Shandong University, and it's my honor to be here to introduce our work, Fusion MSM, a collision-free and arithmetic-optimized FPGA-based accelerator for multiscalar multiplication. Firstly, I'd like to introduce the background of our research. The first question is, why is multiscalar multiplication? In recent years, zero knowledge proof has attracted more interest from both industry and academia. And the figure 1 shows a classical algorithm using zero knowledge proof called GRU16. And we can see there are 3 main operations: number theoretical transform, multiscalar multiplication, and matrix multiplication. And these operations account for different time, and the multiscalar multiplication accounts for the majority of the total time for more than 70%. And the next question is, what is multiscalar multiplication? It can be viewed as an inner product of point vector and scalar vectors. However, in zero knowledge proof, the scale of multiscalar multiplications ranges from 2 powers 18 to 2 powers 26. And the scale and the width of scalar is hundreds of bits, usually 300 to 700. This large scale leads to a significant increase in computational cost and time. And then I will introduce some basic operations used in multiscalar multiplications. On an elliptic curve, there are 2 types of operations, point doubling and point additions. And it is worth noting that the formulae used here are different, and the name method always requires divisions, which is not friendly to the hardware implementations. Finally, I'd like to introduce the classical algorithm using the multiscalar multiplication called the Pippinger algorithm. The core idea of this algorithm is transforming the large-scale multiscalar multiplication into several small-scale multiscalar multiplications. And it contains 3 phases: bucket accumulation, bucket aggregation, and window aggregation. And it also has 2 important features. The first is, compared to other phases, the bucket accumulation dominates the overall time. And the second is, the process between different windows are similar. And this information provides some opportunities for our design. Based on these findings, I will talk about the challenges of the implementation of multiscalar multiplication in hardware. The challenges form a 3-layer structure, and the fundamental layer is finite field arithmetic, especially the modular multiplier. And when the operate size increases, the area and time efficiency always decrease. And based on this arithmetic is point operations on the elliptic curve. As we have introduced before, the name method always requires divisions and separate designs. On top of that is the scheduling. Considering that the cost of 1 point addition unit is always very high, and it is usually designed as a multi-stage structure. So the utilization of this unit is very low, and the clearance may happen in the pipeline. More specifically, previous works always use the Montgomery modular multiplier, but we find some shortcomings in this algorithm. And firstly, we can see that the Montgomery modular multiplication always requires data in the Montgomery domain. So we need the pre and the post computation for the data. And secondly, the algorithm contains 3 dependent multiplications. Although one of them is for arbitrary number and the others are for constants, the resource consumption is very high. As for clearance, here we have shown an example in figure 7 to illustrate its impact on the overall time's performance. And we have give a series of scalar and point, and at time 1, there are 2 points, P1 and P2 belongs to the same bucket with index 1. Remember that the point addition unit is a multi-stage structure, so we can get the result of P1 plus P2 at time g minus 1. And before this time, the content of the bucket with index 1 is invalid. However, there may be another some points belongs to the same bucket with index 1, and this situation is known as collisions. The collision will lower the utilization of the point addition unit, so we need to find a way to solve it. And next, we will talk about our works. Our contributions can be summarized as 4 items corresponding to the challenges. And firstly, we have designed an FPGA-optimized modular multiplier for large integers. We present the hybrid multiplication strategy and multi-bit modular reduction based on lookup tables, achieving lower area and higher speedup over the modular multipliers used in previous accelerators. And based on the efficient arithmetic, we have designed a fully pipelined and unified point addition unit. It can run at a higher frequency and thanks to our efficient modular multiplier. On the top of that, we propose a greedy schedule mechanism which can eliminate the collision-induced stores and enhance the utilization of the point addition unit. And finally, we designed a novel architecture called Fusion MSM, which can achieve the sorter performance across various input size compared to designs on FPGA and ASIC platforms on BLS 12377. So I'd like to introduce our first work, the optimized modular multiplier. There are different implementations of an integer multiplier, and they have their own features. For example, the DSP-based multiplier is usually the fastest, but it needs more DSPs in FPGA. The schoolbook-based multiplier is naive, but it has some natural advantages of parallelization. The Karasuba-based multiplier is usually used in the previous works because it can see one multiplication by using additional subtraction or additions. However, it needs more clock cycles for the data alignment. Based on these features, we proposed a hybrid multiplication strategy. And in short, this strategy adopts different multiplications under different thresholds of operator size in terms of area and efficiency. And the structure of our big integer multiplier is shown in figure 9. And we can find that when the scale is 48 to 58 bit, we use the DSP-based multiplication, taking advantage of built-in multipliers in FPGA. When the scale increases to 96 to 98, we use the schoolbook multiplication to save some time. As the scale increases to 192, we use the Karasuba multiplication to save some resources. And based on this structure, we have designed and optimized some sub-multipliers. And here, we show an example in figure 11. It is the structure of 48 or 49-bit multipliers use DSPs in FPGA. The black dots in this figure represents 1 bit, and the partial products are obtained by using multipliers in DSP. And to accumulate these partial products, we have designed a compressor tree, and it contains half adders in yellow box, 3-to-2 compressors in red box, and 4-to-2 compressors in green box. And we also simplify some compressor at the special case. For example, at the 34th position, the 4-to-2 compressor had no carrying bit, so we can simplify the compressor structure to save some resources. And the other task for the modular multiplication is modular reduction. So we propose a multi-bit modular reduction based on lookup tables. It divides their product into 2 parts. The lower bits are not processed because it's smaller than the modulus P, and the higher bits are processed based on the weights which we can pre-computed and stored in FPGA. And after that, conditional subtraction is carried out to get the accurate result. And the structure of our modular reduction unit is shown in figure 12. However, how to store these weights effectively in FPGA is a critical problem. And as we've seen from the previous algorithm, the initial reduction always contains more branches than the conditional subtraction. So we use the block RAM in FPGA to store the pre-computed weights and use distribute RAM or LUT to store the multiple times of modulus P in conditional subtraction. However, the block RAM in FPGA is consumed in a whole block, so we have tried several cases with different group wise, and the results is shown in table 2. And we can find that when the group width is 9-bit, the number of total block RAM is least. And when the group width increase or decrease, the number of total RAM is always increase. Based on the efficient modular multiplier, we designed a unified and fully pipelined point addition unit. We utilize the unified point addition algorithm in twisted Edwards projection coordinates, and compared to other designs, it contains more modular multiplications, but it doesn't need to transform the intermediate coordinates. Based on the algorithm, we have fine-tuned the 4-processor version of the formulate, and some stamps are placed in advance to avoid additional registers for buffering. And the structure of our fully pipelined and unified point addition unit is shown in figure 14. And thanks to our efficient modular multiplier, it can run at a higher frequency. And the table 6 shows the compression of point addition units in different designs, and we can see that our designs consumes more lookup tables and flip-flops because we adopt the algorithm which contains many modular multiplications. And our design consumes less DSPs because there is only one multiplication in our modular multiplications. More block RAMs are used to store the pre-computed weights, and high frequency and less pipeline is attributed to our efficient modular multiplier. And thirdly, I'd like to introduce our 3-work Claydon-free greedy schedule mechanism. And here, I have shown some figures to illustrate the mechanism. We use scalar to represent the input point and the index to represent the output from the point addition unit. And we also use the register base to record the states of each bucket. The first case is simple because when the point addition unit has no output, we only need to pay attention with the bucket with the scalar. If there is only one point in the bucket, we should read the point from the bucket and send it with the input into the point addition unit. And the situation becomes more complex when the point addition unit has a valid output. A special case is that the index is same as the scalar, and in this case, we just set the points into the point addition unit, and the states of each bucket still remain. However, when scalar is different from the index, we should check the states of each bucket. If one of them is empty and the other bucket is full, we will read the point stored in the full bucket and send it with the input into the point addition unit. If both of the buckets are full, we will read the point stored in one of the buckets and send it with the input into the point addition unit. And the other full bucket is also read into the FIFO. And when the point addition unit is free, we will read the content of FIFO and handle the stored points. As for the bucket aggregation, the schedule mechanism is shown in figure 17. We just read the bucket with the highest indexed to the lowest indexed. And the time consumed in this phase is dependent on the width of window. And finally, I will introduce our architecture of Fusion MSM. It contains several components, such as FSM controller to control the overall process, and the state monitor to store the states of each bucket. The PADD unit is the main computational unit for the point operations. And finally, I will talk about the results and some discussions. And compared to the FPGA-based and ASIC-based works on BLS 12377, our work achieves the SOTA performance. And compared to the GPU implementations, it delivers comparable performance at some degrees, but with a lower power consumption. More specifically, compared to the ASIC-based work PipeZK, our work supports more degrees and exhibit more efficient. And it is attributed to our unified point addition unit because we do not need to design the point addition and point doubling unit separately. And the schedule strategy can handle the points immediately and improve the utilization of the point addition unit. And compared to GPU designs, our design delivers a comparable performance at some degrees, but with a lower power consumption. This is mainly because that GPU is always designed for high performance computation, and it contains many CUDA cores, which can enable a higher parallelism. Compared to the existing FPGA works, it can achieve the SOTA performance, and the reasons are threefold. For the modular multiplier, our design contains fewer multipliers and consider the trade-off for different thresholds of operate size. As for the point addition unit design, our design do not need to transform the coordinates in the halfway. And the greedy schedule mechanism can improve the utilization of point addition unit and avoid the continuous increase in queues. And in this slide, we show the resource consumption of Fusion MSM and compared it with other designs. And obviously, it consumes fewer flip-flops and DSPs, and the minimum URAM usage stems from our small window width and the pre-computation strategy we adopt in the picture algorithm. However, the RAM consumption is a little high because we need to store the weights and use it in the modular multiplication. And that's all, and thanks for your attention.
Questions for the speaker? I have one quick one about the results. You explain why you use more VRAM, but why you use fewer flip-flops and DSP?
Okay. I think the main reason is that our modular multiplier contains only one multiplications, because in previous works, if you use Montgomery multiplication or Barrett multiplication, you will need more multipliers, at least 3, although one of them is for arbitrary and the rest of them are for constants, but it still needs some resources. And the DSPs is responsible for the multipliers, especially at the scale of 48 to 58 bit. And as for the flip-flops, in our design, the flip-flops are mainly consumed for the higher frequency, because the flip-flops can use to buffering the data. And in our design, our point addition unit contains more modular multiplications, but the modular multiplication contains less multiplication. So the total outcome of this optimization leads to the fewer flip-flops and this DSP use.
Thanks. We have questions? Yes.
So thanks for the talk. I would have one or two questions. So like the first one is like you presented that the frequency of your multiplier is like 500 megahertz. Like, is there a reason why you couldn't get the whole design to that frequency? Because I think you're running it on 350 or like something like that. And the other question is like, it seems like your resources are like much smaller than the other designs. In this case, you should probably be able to scale it much better because like use less DSPs, so like probably like instantiating more elements on that chip, and then doing some in parallel. Would that help?
Do you mean that the frequency of our modular multiplier is different from the
Yes, exactly.
our final frequency?
Yes, exactly.
Oh, thanks for a question, and it's really a good question. And in our design, we start from the design of the multipliers because we have find the challenges in the arithmetic layer. And the results of our point addition unit is 500, and the overall frequency is limited by the control unit because by the control unit, because the Pivot algorithm contains three main phases, and the architecture here, the data RAM and the FIFO will affect the overall system's frequency. So although our multipliers can run at a higher frequency, in fact, in our experiment, it can run at a higher frequency than the reported frequency. But the overall system limits its efficiency, and the architecture of this and the schedule mechanism limits the higher frequency to our final outcome. It's 345.
Would it be possible then to maybe like do some clock domain crossing, that you like still use the fast multiplier and just like feed more data into it? So then your design would be faster probably?
Sorry, could you please speak a little slower?
Oh, sure. So like would it then be possible to just run your multiplier faster and then just do some small clock domain crossing beforehand? And then your design would be like faster by like probably like one like third?
So do you mean our multipliers consumes less clock cycles, and this leads to the final low latency of our design?
No, it was meant more like, since like it can run faster, you could probably like still run it on a faster frequency.
I understand. You mean that the multiplier can run at a higher frequency, so maybe our architecture can run at a higher frequency.
Oh no, like just like still using it on the like the architecture on a smaller frequency and just like letting one model run faster, because then probably your performance would even be better than now, if I'm not wrong.
Oh yeah. Oh yes. I understand your opinion. Your opinion is about to lower the frequency of our multiplier, and it is useful for our architecture.
Oh no, it's fine. Like what I just meant was like if you maybe run it on different frequencies, because like your multiplier is quite efficient it seems, and it's quite slow, so you could probably like utilize it more if it's possible, if it would help.
I understand. Your opinion is about to use the multiplier more frequently?
Yeah.
Yes. I think I will consider it as our future work, because it might might improve the performance. Thank you.
Thank you for your presentation. I have two questions. The first one is, can you go to your slides 24?
24. Okay.
Yes, we noticed that you have a DRAM attached to your architectures. And what's the throughput requirement of your MSM to use such DRAM?
Do you mean the requirements of the RAM?
Yes, the throughput, the bandwidth of the RAM.
Okay. And in our design, we regard the DRAM as how to say, the bandwidth requirements of the RAM is very high in this architecture, and we use the ping-pong operations to lower the requirements of the RAM. And in our design, the DRAM is responsible for storing the points on the BLS 12300 and 77 curve, and the point is the coordinates of point is input into the structure in one clock, and the scalar is input with it, and the bandwidth of the RAM also impacts the overall performance. So our next work is considering how to lower the requirements of the bandwidth of the RAM and to improve the overall performance. And just learn from the lecture on the morning, OPTI MSM, they have proposed a new idea about to lower the requirements of the RAM and reduce the off-chip memory.
And do you have a specific number of that throughput or bandwidth of your DRAM?
Sorry, I'm not responsible for this part.
So do you also consider the roofline model for your design?
Roofline model is.
Oh, never mind. So my last question is that so we noticed that like you said, we have two MSM implementation this morning, and which was published at this year CHES issue 2, and there was another MSM implementation published at the issue 1 of CHES. But on your slides page 29, you are not comparing with them. And can you comment on that? Or do you have some comparison with them?
Okay, and thanks for a question. The two multiscalar multiplications works published in this CHES conference, one of them is on the CPU and use the SIMD instructions. And in fact, the CPU always had a lower performance because the CPU is responsible for the instructions. And the main task for the CPU-based implementation is how to reduce the memory. And as for the OPTI MSM, it is evaluated on the BLS 12300 and 81 curve. And this curve is different from the BLS 12377 because BLS 12377 curve has a special property. It can transform into the twisted Edwards curve, and the point addition is more efficient than the operations on the BLS 12381. So the compression is unfair, and we are going to, in the future, we are going to apply our strategy on this curve and try to find the advantages or disadvantages compared to other similar designs. And that's all.
Thank you.
Okay, thank